Hello everyone. So this is the fourth hour of rotational motion, and in this hour I'm going to focus on only one thing, which is Newton's second law for rotational motion. In the last hour we learned what is Newton's second law for rotational motion. We said that just like Newton's second law for translational motion is the net external force acting equals to dp by dt. Similarly, we can say that the net external torque acting equals to the rate of change of angular momentum with respect to time. For a body doing pure rotational motion, we can write torque equals to d I omega by dt. You can pull I out of the differentiation and you can write torque equals to I times d omega by dt, and d omega by dt is alpha. So you get torque equals to I alpha. So today we will be focusing on questions based on torque equals to I alpha. This will be primarily a question hour. So stay focused, and I know you will remember answer to all the question at the end of the session. So the first question coming up. Question is, there is a ball of mass m projected with a speed v at some angle theta with the horizontal. Question is, determine the angular momentum about the point of projection at any time t. We wrote angular momentum about the point of projection when the ball is at the maximum height. We have written the angular momentum about the point of projection when the ball is just about to land. This time I am asking you, what is the angular momentum of the ball about the point of projection at any random time t? So now one can write the position coordinates at any random time t. One can write velocity at any random time t. We know that the position coordinate at any random time will be the displacement in horizontal direction, which is v cos theta into t I cap, plus the displacement in vertical direction, which is v sin theta into t minus half gt square j cap. This is the position vector with respect to point of projection at any time t. The velocity vector at any time t will be v cos theta I cap plus v sin theta minus gt j cap. So multiplying the velocity vector with the mass, you will get the momentum vector. So once you know momentum vector, you know the position vector, you can take their cross product to find the angular momentum. But don't you think this will be a very tedious process? So we have got an easy solution, though this tedious process gives the same answer as the easy solution. We know that we have just learned torque equals to dl by dt. If I ask you what is the torque on this mass projected about the point of projection at any time t, so you'll say torque about point of projection at any time t, let's say at any time t particle is at position shown. The force of gravity, which will be downwards mg. The torque of this force of gravity can be written as by extending the line of action of force times the distance perpendicular. In any time t, how much horizontal displacement the particle would have made? So you will say, sir, the horizontal velocity is constant, v cos theta, as there is no acceleration in the horizontal direction. So in any time t, the horizontal displacement will be v cos theta into t. So the torque about the point of projection at any time t will be force times length perpendicular. Once you know the torque at any time t, you can write angular momentum. How? In place of torque, you can write dl by dt. So you can write dl by dt equals to mg into v cos theta into t. Bring the dt up here and integrate. You will get your angular momentum at any time t. So at any time t, the horizontal displacement will be v cos theta into t. So you can write the torque equals to mg into v cos theta t, or better dl by dt equals to mg v cos theta time t. Now bring this dt up, and on integration you will get dl equals to mg v cos theta into t dt, integrating both the side, angular momentum from 0 to L and time from 0 to t. Integration of t dt gives you what? T square by 2. Integration of dl gives you what? L. So you will get better after integrating. The angular momentum at any time t about the point of projection is mg v cos theta into t square by 2. Again, you can write position vector at any time t. You can write momentum vector at any time t. You can take cross product, but that will be tedious process. So this is a shorter process. Just keep it in mind. So moving on to the next example. Today we will be just doing examples one after another. So the example goes like, there is a horizontal rod and it is hinged at one of its end. Question is, determine the angular acceleration produced in the rod due to the force of gravity just after release. So what will be the angular acceleration of this rod just after the release? So you will say, sir, just after release, there will be only two forces acting on this rod. One will be the force of gravity, try to turn it clockwise. One will be the force by the hinge. But about the hinge, the force by the hinge won't produce any torque because its R is 0. So there will be only one force producing the torque, and that will be the force of gravity. Now the torque produced by this force of gravity will be force times length perpendicular. So that will be mgl by 2. So you can say the torque about the hinge equals to moment of inertia about the hinge into alpha. The torque about the hinge equals to moment of inertia about the hinge into alpha. So we can say torque equals to I alpha. The torque about the hinge will be because of the force of gravity acting at a perpendicular distance of L by 2. So the torque has to be equals to mgl by 2. And this torque about the hinge has to be equals to moment of inertia about the hinge into alpha. So you can say mgl by 2 equals to moment of inertia about the hinge will be how much better? What will be the moment of inertia of a rod about an axis passing through its end and perpendicular to its length? ml square by 3, not 12, 3. About the axis passing through center, it is ml square by 12. About the axis passing through the end, it is ml square by 3. So the torque about the hinge, mgl by 2 equals to ml square by 3 into alpha. So easy. Now, bachcho, cancel out m and m. So you will get alpha equals to, and 1L with 1L, alpha comes out to be 3g by 2L. So easy. Alpha comes out to be 3g by 2L. There is one more thing which is important and you should know. What is the acceleration of the center of mass in this case? So you will say, sir, we know that V equals to omega r for a body doing pure rotational motion. The velocity of any point on the body at distance r is given by omega r. Similarly, if the rigid body also has an angular acceleration alpha, then the tangential acceleration of any point can be said to be alpha r, given that the point is at distance r. So we can even say acceleration of center of mass will be, since now we know alpha and we know the distance of center of mass from the hinge, we can say that tangential acceleration has to be equals to alpha into r. The angular acceleration we know comes out to be 3g by 2l, and we know that r for center of mass is L by 2. So you get 3g by 2l multiplied by L by 2. Now cancel out L and L. What you get is 3g by 2 multiplied by 1 by 2, that is nothing but 3g by 4 downward. So just after release, the center of mass of the rod will have a downward acceleration of 3g by 4. We will use this later to find the force by the hinge. But let's move on to the next example first. So now the similar type of question, but rather than having a rod, we have a disc. So the disc is released from the horizontal position as shown. Horizontal position means the center of mass of the disc is at the same level as the hinge when released. Determine the angular acceleration and acceleration of center of mass of disc just after the release. So what will be the alpha of the disc about the hinge, and what will be the acceleration of center of mass just after the release? So you can visualize the forces acting on the disc just after the release. There will be a force of gravity downwards that can be assumed to be acting at the center of mass, and there will be a force by the hinge. Will the force by the hinge produce any torque about the hinge? No sir, R is 0. So there is only one force producing torque about the hinge, and that is the torque of force of gravity. From Newton's second law for rotational motion, if we have a rigid body doing pure rotational motion, we can say that torque equals to I alpha. The torque here about the hinge is that of the force of gravity, and that torque will be force times length perpendicular. So the torque will be nothing but mgr. Now the second thing you need to focus upon is what is the moment of inertia about the hinge. Moment of inertia about the hinge. So if you have this disc, the moment of inertia about its own axis will be mr square by 2. Moment of inertia about this axis passing through the periphery can be found using the parallel axis theorem. So that will be equals to mr square by 2 ICM plus md square mr square. So that becomes better 3 mr square by 2. This is the moment of inertia about the hinge. So you can write torque acting equals to I into alpha. I can be written as mr square by 2 about the center of mass plus mr square into alpha. So this whole quantity becomes 3 mr square by 2. So you can write mgr equals to 3 mr square by 2 into alpha. Cancel out 1 r with 1 r, 1 m with 1 m. What you get is alpha equals to 2g by 3r. So angular acceleration is 2g by 3r. So we know that just after release, the angular acceleration of this disk will be equals to 2g by 3r. But they have asked me one more thing. What is the acceleration of the center of mass just after release? So just after release, there will be only tangential acceleration. How much? Sir, we know the alpha and we know the distance of center of mass from the hinge, which is r. So we can say that the tangential acceleration just after release has to be equals to alpha into r. So center of mass is at distance r from hinge. So we can say its tangential acceleration just after the release will be equals to alpha into r. That will be equals to 2g by 3r, which is what we got alpha times the distance r. Cancel out r and r. You get the downward acceleration of center of mass just after release is 2g by 3. Easy. So now we are going to use these two examples of rod and disc, but this time we will try to find the force by the hinge. So the question is, find the force by the hinge on the rod just after the release of rod. So we have already done this question. What will be the alpha of the rod? What will be the acceleration of center of mass? This time the new question is, we need to find what is the force by the hinge on the rod just after the release of rod. So we will say, if we have this rod has mass m and length l, the torque about the hinge is the torque equals to I alpha. So mgl by 2 equals to ml square by 3 into alpha. Cancelling out one term of m, m, l, l, we got that alpha came out to be 3g by 2l. And since we know that the center of mass is at a distance l by 2 and alpha is known, we can write acceleration tangential as alpha into r, and r will be l by 2. So you get acceleration of center of mass just after release will be 3g by 2l into l by 2, and that what we got as 3g by 4 downwards. Now look at the forces acting on the rod. You know that there is a downward force of gravity trying to pull it down. And you know that there will be an upward force by hinge, let's call it M. Now under the influence of these two forces, the center of mass accelerates down with an acceleration 3g by 4. Remember, in the beginning of center of mass, I said that center of mass is representative point to understand the translational motion of the body. All the forces acting on system of particles, here you have got a rod, it has got infinite number of particles. All the forces acting on a system of particle can be assumed to be acting at the center of mass, and the net force on the system of particle equals to mass of the system times the acceleration of center of mass. Here we know that just after release, the acceleration of center of mass will be 3g by 4 down, and the net force acting on the system will be mg minus n. So you can write the equation as mg minus n. The net force in direction of acceleration equals to mass into acceleration of center of mass 3g by 4. Once you have written this, game over. So now from here you can say the normal reaction will be equals to mg minus 3mg by 4, and that will be equals to mg by 4. So just after release of the rod, the hinge applies a force equals to 1/4 the weight of the rod. Just after release of the rod, the hinge applies a force equals to 1/4 of the weight of the rod. So now let's do the same type of question but for disc. So question is, there is a disc released from the level that the center of mass is at the same level of the hinge. Find the force by the hinge on the disc just after the release of the disc. Find the force by the hinge on the disc just after the release of the disc. So you will say, look at the force profile just after the release. There is a force of gravity downward, yes. There will be some force by the hinge upward, let's call it n. Our mission is to find out this n. We know what is the alpha of the disc. We know what is the acceleration of center of mass of the disc. I can simply find out n just by making the force equation in the vertical direction. All the forces acting on the system of particle can be assumed to be acting on the center of mass, and the net force in direction of acceleration equals to mass times acceleration of center of mass. So we have already done, but doing it again. So using torque equals to I alpha, we can say that the torque about the hinge is mgr, only due to the force of gravity, a force of gravity mg acting at distance r. This has to be equals to I into alpha. The moment of inertia about the hinge will be mr square by 2 plus mr square. So that will be 3 mr square by 2 into alpha, and we have already done this. On solving, we get alpha equals to 2g by 3r. Once you know alpha, You can find out acceleration of center of mass. Since center of mass is at distance r from the hinge, you can say that acceleration of center of mass has to be alpha into r. So 3g by 2r into r. So that gives you 2g by 3 downwards. Now once we know acceleration of center of mass is 2g by 3 downwards, and we know that there is a downward force mg, upward force n. So you will say mg minus n, the net downward force, equals to mass times acceleration m into 2g by 3. So we will get on rearrangement n equals to mg minus 2 mg by 3, and mg minus 2 mg by 3 comes out to be equals to mg by 3. So this is how you can find out the force by the hinge in each case. Sir, to find force by the hinge, what to do? Very simple. First, make the torque equation. Using the torque equation, find out alpha. Once you know alpha, find out ACM. And once you have ACM, then apply the force equation. This is how you find the force applied by the hinge. Using torque equals to I alpha, find alpha. Then using alpha, find acceleration of center of mass. Then using acceleration of center of mass, find the force by the hinge. So now the type of question we are going to do are very standard question, and I promise you, you will remember answer to all these questions, but keep listening carefully. So the question is, there is a pulley with two blocks of mass m1 and m2. m2 is accelerating down, m1 is accelerating up. If m2 is accelerating down, m1 is accelerating up, who has to be heavier? So you will say, sir, if m2 is accelerating down, m2 has to be greater than m1. So obvious. But sir, this is not Newton's laws. We are learning rotational. So here something has to rotate. So what will rotate? The pulley, right? So here, when m2 comes down, m1 goes up. If you visualize this system, then how the pulley must be rotating. You will say, sir, if m2 goes down and m1 goes up, the pulley must be rotating clockwise. So this pulley has to be rotating clockwise. Now, this is not the pulley of Newton's laws, which was massless. This is the pulley of rotational. It has some moment of inertia. So question goes like this. If the spring does not slip over the pulley, and the pulley has a moment of inertia I, determine the acceleration of the blocks. So now the pulley also has some moment of inertia I, and you need to determine the acceleration of the blocks. So you will say, okay, sir, first thing, as the m2 accelerates down, m1 accelerates up. The pulley must be turning clockwise. If I ask you on which side of pulley the tension has to be higher, if I let's say mark out here the tension to be T1 and here the tension to be T2, and I tell you that the pulley is rotating clockwise, which tension has to be higher, T1 or T2? So you will say, sir, T1 is trying to turn the pulley anti-clockwise, while T2 is trying to turn the pulley clockwise. If the pulley turns clockwise, then T2 has to be greater than T1, because it will be providing a net torque to turn it clockwise, right? Now, let's see the solution. So let's say on the right hand side string, the tension is T2. On the left hand side string, the tension is T1. It's really easy question. It's just that we have added one more pulley. Since the pulley has moment of inertia, the tension on both the side is not same. Since the tension on both the side is not same, we can't simply write the equation as m2 minus m1 into g upon m1 plus m2. So we will have to write equation for each individual, the second block, the first block, and for the pulley. So first of all, look at the forces acting on this block of mass m2. On the block of mass m2, there is a downward force of gravity m2g. There is an upward force of tension T2, and under the influence of only these two forces, it moves down with an acceleration A. How will you write the force equation? Sir, the net force and direction of acceleration equals to mass into acceleration. So I can write the net force downward, m2g minus T2 equals to m2 into A. So m2g minus T2 equals to m2 into A. This is the force equation on the block of mass m2. Now look at the forces acting on block of mass m1 and write force equation on it. So for the block of mass m1, there is upward tension T1, there is downward weight m1g. So upward tension T1, downward weight m1g, and under the influence of these two forces only, it is going up with an acceleration A. You will write the force equation as the net force in direction of acceleration T1 minus m1g equals to m1a. So T1 minus m1g equals to m1a. Now it's time to write the equation on pulley. When we write the equation on pulley, we will look at the torque provided by different force on the pulley. So we will say, look at the pulley. Let's say the pulley has a clockwise angular acceleration alpha. Now, from the right hand side, tension is T2, it is trying to turn it clockwise. From the left hand side, tension is T1, it is trying to turn it anti-clockwise. Now, the torque of this tension T2 will be T2 force times length perpendicular, T2R clockwise. The torque of this tension T1 will be T1R anti-clockwise. The net torque equals to moment of inertia into alpha. The net torque will be T2R minus T1R. The net torque in the sense of alpha has to be equals to I into alpha. So you will write, bachcho, T2R minus T1R equals to I into alpha. There is one more condition given in the question. Condition is that the string does not slip over the pulley. If the string does not slip over the pulley, it means that at the point of contact, they have the same velocity. So if I say that the velocity of pulley is v and the velocity of string particle here is u, I can say if they are not slipping, v equals to u. Differentiating it both the side, I can say dv by dt equals to du by dt. It means that the acceleration of a point on the periphery of the pulley, the acceleration of a point on the periphery of the pulley, which acceleration? Tangential acceleration, has to be same as the acceleration of the string. We know that string is connected to block and the block has a downward acceleration a. So this point on string will have a downward acceleration a. And the point on the periphery of the pulley should have the same tangential acceleration. So it will also have an acceleration a. So we can say that the tangential acceleration of a point on the periphery of pulley will be equals to alpha into r. So alpha into r equals to a. This is the condition for no slipping of the string on the pulley. So from here you get the fourth equation for no slipping of string, a equals to alpha r. When you solve these four equations, where you have got four variable t1, t2, alpha and a, and you solve for a, you get that a comes out to be m2 minus m1 into g upon m1 plus m2 plus I by r square. If I say, beta, forget that the pulley has some moment of inertia. Think that this is a massless pulley and we are doing question of Newton's laws. And I ask you what will be the value of a, you will say, sir, for Newton's law, pulley massless, acceleration is m2 minus m1 into g upon m1 plus m2. Remember that on solving these four equations, you got the result as m1 minus m2 into g upon m1 plus m2 plus I by r square. So remember this step. Add an extra mass to the mass of the system, and that is nothing but the moment of inertia of the pulley divided by its radius whole square. So add an extra mass to the mass of the system, which is equals to I by r square, and you can do your own Newton's laws all over again. So let's understand this more from another example. Let's say this time they have given me this system. There is a block of mass m1, there is a block of mass m2, but this time again the pulley has some moment of inertia and the string is not slipping over the pulley. So question is, find the acceleration of block if the pulley has moment of inertia I and radius r. What will be the acceleration of the blocks? So again you will say, sir, let's assume some forces acting. Let's say the tension here in the string is T1 and the tension here in the string is T2. So in horizontal part we have taken tension as T2, in vertical part we have taken tension as T1. Now if the acceleration of m2 is downwards a, then the acceleration of m1 has to be horizontal a, and let's say this pulley has some angular acceleration alpha. For no slipping, I can say that the tangential acceleration at a point on the periphery of pulley will be equals to alpha r has to be equal to acceleration of string at that point, which is a. You can write the force equation on both the blocks and you can write the torque equation on the pulley. So doing it quickly one by one. So first of all, look at the block m2, downward force m2g, upward force t1. So I will write the force equation as m2g minus t1, the net force in direction of acceleration equals to mass m2 into acceleration a. Now look at the forces in the direction of acceleration on m1. So on m1 there is only one force of tension t2, so you will write t2 equals to m1a. Now you can make the torque equation on the pulley. On the pulley here there is a tension t2. This tension T2 acts at a distance r from the center and is trying to turn it anti-clockwise, while the tension T1 is trying to turn it clockwise. If we know that this pulley will turn clockwise, We know that beta T1 has to be more than T2. So you will write the net torque equals to T1R minus T2R, and this net torque has to be equals to I into alpha, and again the condition for no slipping, A has to be equals to alpha R. On solving these four equations, you get the answer as m2g by m1 plus m2 plus I by r square. If I would have told you this pulley is massless and we are doing a question of Newton's laws, and here we have a block of mass m1, here we have a block of mass m2, and I ask you determine the acceleration of both the blocks. So you will say, sir, the net driving force will be m2g and the acceleration has to be simply m2g by m1 plus m2. Notice that here we got an extra term in the mass of the system, and that term is I by r square. So just remember to add an extra term equals to I by r square, and it's just like Newton's law. So you won't have to solve equations in the paper, and that will save up a lot of time. So practicing more. So now the same type of case but on an incline, so it looks tough. So there are two blocks of mass m2 and m1. Now if I tell you that m2g is greater than m1g sine theta, it means that the pulling force here m2g is greater than the pulling force here m1g sine theta. Then m2 will move down, m1 will move up the incline, and the pulley will rotate clockwise. So question is, if m2 is greater than m1 sine theta, if m2 is greater than m1 sine theta, moment of inertia of pulley is I and radius is r, and string does not slip over the pulley, find the accelerations of the block. So let's say this block m2 comes down with an acceleration a, this block m1 goes up the incline with an acceleration a, and the pulley rotates with an angular acceleration alpha. Assume tension to be T1 and T2, so you get this case. So here assume tension to be T1 and there assume the tension to be T2. Now I ask you a simple question, which one has to be greater, T1 or T2? So you'll say, sir, look at the pulley. Here a force T2, here a force T1. T2 tries to turn the pulley clockwise, T1 tries to turn it anti-clockwise, but since the mass m2 goes down, mass m1 goes up the incline, the pulley will turn clockwise, and if the pulley turns clockwise, it means that T2 has to be greater than T1. So now we will again make the force equation on each block. First, on the block of mass m2, there is an upward force T2, downward force m2g. You will write the net force in direction of acceleration equals to mass into acceleration, so m2g minus T2 equals to m2a. Second equation you can make on this block of mass m1. Look at the forces on the block of mass m1 along the incline. So there is an upward force T1 up the incline. There is a component of force of gravity trying to move it down the incline, which is m1g sine theta. And under the influence of these two forces T1 and m1g sine theta, it goes up with an acceleration a. So you will write T1 minus m1g sine theta equals to m1a. Now the third equation will be on the pulley. On the pulley there is a tension T2 and a tension T1. The T2 tries to turn it clockwise, T1 tries to turn it anti-clockwise. So you will get T2R clockwise torque minus T1R anti-clockwise torque equals to I into alpha. And the fourth equation, that is the equation for no slipping, and that equation will be equals to A equals to alpha R, and on solving these four equations, we get the answer that acceleration comes out to be m2 minus m1 into sine theta whole multiplied by g upon m1 plus m2 plus I by r square. If again I would have asked you the same question in Newton's laws and would have given you the same condition, m2 is greater than m1 sine theta, but the pulley is massless, so your answer will be m2g minus m1g sine theta. So m2g minus m1g sine theta upon m1 plus m2. Here you just get an extra term of mass, which is moment of inertia of pulley upon its radius whole square. So these type of questions are not tough because you won't have to make the equation, you will directly remember the acceleration. Then sir, why are you even teaching us how to make the equation? Reason being, sometimes in the question they know that the student might have remembered the answer of acceleration. So they might ask you determine the tension in this string or determine the tension in this string. For that you should know how to make the equation. Okay, or they might ask you what is the alpha of the pulley. So alpha of pulley has to be nothing but A by R. If you remember A, divide it with R, you will get alpha. Okay, moving on. Now the case is this. A cord is rolled around a circle. So you took a wire, a string, and rolled it around a cylinder, and the cylinder is released from the position as shown. Determine the acceleration of the cylinder. If it has a mass m, the mass of cylinder is m, moment of inertia about its own axis I, and a radius r. So if you have got this cylinder and here connected with a string which is fixed to the ceiling, you need to find the acceleration of the cylinder as it comes down. So what will be the forces acting on this cylinder? So assume that there will be a force of tension for sure, and there will be a force of gravity. Assume that under the influence of these two forces, it gets an angular acceleration alpha and a translational acceleration A downward. The center of mass gets a translational acceleration A downward. So making the force profile, assume that it gets a downward acceleration A, angular acceleration alpha, the forces are T and mg. Now you will say about its own axis, about the one where we know that moment of inertia is I, the torque of the force of gravity about this axis is 0. Why? Because the force passes through. So there will be only one force producing the torque. Which force? The force of tension. The torque of this force of tension will be T into R. So you can write both the force equation as well as the torque equation. So you will write the force equation, mg minus T equals to ma. It's not a tough thing. Second, you will write the torque equation, that T into R, the net torque equals to I into alpha. And then the condition of no slipping. If there is no relative motion at the point of contact, then beta A has to be equals to alpha R. When you solve these three equations, you get the acceleration to be equals to mg upon m plus I by r square. So if you release a block, its acceleration is g down. Why? Because you will say acceleration equals to force mg by its mass. Add an extra term of I by r square to the mass, you get the acceleration. That's how simple it is to remember all these results. They might know that students have remembered the acceleration. So they might ask, what will be the speed of the cylinder once it has moved down by a distance h? So you'll say, easy. If you take the initial velocity to be 0 and the acceleration is known, then the speed after moving down a distance h will be root 2ah. They might ask you tension. If you remember the acceleration directly, find it out directly using this particular method and then substitute it in the equation mg minus T equals to ma to find the tension. So they might change the question here and there, and you have to be smart enough to answer it quickly because you get only 1 minute to answer the question. So you need to remember the acceleration. If they ask acceleration, good. If they ask something else, get the acceleration quickly and then using it find the other data point. Let's see the next example of the same type. This time we have a cylinder type object and it has been suspended from its center and a string is wrapped around it, and then this string is connected to a block. Question is, a massless string is wounded round a cylinder of moment of inertia I and connected to a mass m. Question is, what will be the acceleration of this block once released? So this is again a simple question and you are going to remember the answer. But first bachcho, look at the force profile both on the cylinder on which the string has been wrapped around and of the block. So if the string does not slip, find the acceleration of the block. So given that the string is not at all slipping, what will be the acceleration of this block? So think of the force profile for the cylinder. Now on cylinder there will be force by this string. There will be its force of its own weight and there will be a force of tension. But the force of tension is the only one producing a torque, because the force by this top string and the force due to its own weight passes through the axis, so their torque is 0. So torque is only produced by this tension T. So making the torque equation, you will say the net external torque T into R, tension into radius, equals to I into alpha. So net external torque equals to I into alpha. This is the first equation. Now visualize the block. On the block, you will have the same tension. And if the block has a downward acceleration A, you can write the force equation as mg minus T equals to ma. Now, for no slipping, you will make the same old equation. For no slipping, A has to be equals to alpha R. When you solve these three equations for the three variable t, alpha, r, after solving you get a equals to mg upon m plus I by r square. So if you release a block directly to fall, its acceleration is mg by its mass. That's why you get g downward. Now beta, in the case of pulleys, when you have one pulley, add up an extra term of I by r square. And that's how you get the answer. Once you remember the acceleration, you can find out tension easily. Mg minus t equals to ma. If you remember the acceleration substituted, you will get tension. If they ask you what will be the speed of this block after a time t, so you will say, sir, I know the acceleration. So if they are asking me velocity after a time t, I will say velocity has to be acceleration into time. If they ask you what is the velocity of the block after falling through a distance h, so from the third equation of motion, you will say v square minus 0 square equals to 2ah. So v has to be equals to root 2ah and substitute a from here. If they ask you what is the omega of this cylinder once the block has fallen through a height h, so using the third equation of motion, you will write v square minus 0 square equals to 2 times acceleration into h. Substitute the acceleration from here. Once you know what is the speed of the block, you can write for no slipping as a equals to alpha r. On integrating, we will get v equals to omega. So the speed of the block has to be equals to omega of the disk into r. So you will get omega as v by r. So find out v using third equation and then get omega using v by r. But the most important step is that you should remember the acceleration. So revising all the cases we have done till now on a single page. The first case, a block of mass m2, a block of mass m1. In this case, acceleration came out to be m2 minus m1 into g upon m1 plus m2 plus I by r square. Just add up an extra term of mass I by r square. The second case, here the driving force was m2g. So you will write m2g upon m1 plus m2 plus I by r square. The third case, here the driving force was m2g minus m1g sine theta. So the acceleration came out to be m2 minus m1 sine theta whole into g upon m1 plus m2 plus I by r square. Add an extra term of mass equals to I by r square. Now the fourth case, here the driving force was mg and the acceleration came out to be mg upon m plus I by r square. And the last case we have learned is this case where we have a cylinder and a cylinder on which a string is wounded connected to a block. Here the driving force is mg and the acceleration comes out to be mg upon mass of the block plus I by r square. So easy to remember. If you can remember all these things quickly, you will be able to answer the question faster. So now let's move on to the next thing and talk about the energy conservation in the case of rotational motion. So we know that for a body doing translational motion means at any goddamn instant, each and every point on the body has the same velocity. So if a body does translational motion, then its kinetic energy is given by half mv square. Similarly, if a body does pure rotational motion, and let's say the body rotates with an angular velocity omega about an axis. So we say that if the body performs pure rotational motion about a given axis with an angular velocity omega, then its rotational kinetic energy is given by half times moment of inertia about the axis into omega square. Remember this. There is one more thing which I tell students to focus here, and that is that how do you write work due to a torque? We write work due to the force by dw equals to f dot ds. Beta, torque is analogous to force. And what is analogous to displacement? Sir, angular displacement. So for angular motion, we write the infinitely small work done equals to tau dot d theta. Just remember this. And for rotational motion, we write the infinitely small work done equals to tau dot d theta, or you can integrate it both the side. You get that the work done equals to integral tau dot d theta. I will use this somewhere in magnetism, that the work done by magnetic force equals to the torque because of the magnetic field multiplied by the angle rotated. Integration of multiplied by the angle rotated. So let's do a simple question based on. There is a rod of mass m and length l. The rod is hinged at one end and released from the horizontal position. Determine the angular velocity of the rod as it becomes vertical. So rod is released from horizontal position. You have to tell the omega of the rod as the rod becomes vertical. So you will say, sir, think of the initial condition and the final. Initially, the rod is horizontal, and finally, the rod is vertical. When the rod will be vertical, what will be the angular velocity of the rod? This is something we need to find. Yes. So how to do? Sir, easy. As the rod moves down, the force of gravity pulls it down. The work done by force of gravity will be equals to force times displacement in the direction of force. Whose displacement? The displacement of the point at which you are assuming the force to act. Sir, we are assuming the force of gravity to act at center of mass. So should I just take the vertical displacement of center of mass? Yes. The center of mass will move a vertically downward distance L by 2. It will move on an arc, but from initial to final, it will move a downward distance L by 2. So the work done by force of gravity will be simply mg L by 2. Sir, the hinge also applies some force now at each instant, yes. Then why are you not writing the work done by hinge? I won't use the work done by hinge because when I write dw equals to f dot ds, dw equals to f dot ds. What is f? Force. What is ds? The infinitely small displacement of the point of application of force. As the rod moves, the hinge applies force at the point near the hinge, but those point does not have any displacement. That's why the work done by hinge force will be zero. So there will be only work done by one force, and that is the force of gravity. So we can say as the rod goes from the horizontal position to the vertical position, work done by all the forces equals to change in kinetic energy. Since in this case the rod is performing pure rotational motion, we will say work done by all the forces equals to change in rotational kinetic energy. So work done by only one force, and that is the force of gravity, which is equals to mg L by 2. As the center of mass of the rod moves down by a distance L by 2, the work done by force of gravity will be mg L by 2, and this has to be equals to half I omega square. Now the rod performs pure rotational motion about the hinge. Moment of inertia about the hinge is ml square by 3. So you will write this to be equals to half I omega square, and in place of half I omega square you can write half ml square by 3 into omega square. The 2 and 2 get cancelled, 1 L and L get cancelled, so you get omega equals to under root of 3 and m get cancelled, 3g by L. So omega comes out to be under root of 3g by L. Once you know what is the angular velocity of the rod as it becomes vertical, you can even find what will be the speed of the terminal of the rod as it becomes vertical. So just the way I have been using acceleration tangential equals to alpha r, we can even use now velocity equals to omega r. So omega will be root 3g by L, and the distance of the end point from the hinge is L. So you will say the speed of the tip of the rod. Once you know omega, you can find even the speed of the tip of the rod. The speed of the tip of the rod is nothing but omega into L, that will be root 3g by L into L, that becomes root 3gl. So that will be the speed of the tip of the rod as the rod becomes vertical. So let's move on. Now let's talk about angular momentum conservation. When do you do momentum conservation? So when the net external force is zero. When will you do the angular momentum conservation? When the net external torque is zero. So for a rotating body, the torque equals to the rate of change of angular momentum with respect to time. If the net external torque is zero, if there is no net external torque acting, then you will say that dl by dt is zero. If dl by dt is zero, it means that L is constant or angular momentum is constant, it is conserved. Just like if the net external force is zero, we say that momentum is conserved. So when do you do momentum conservation? When the net external force is zero. When do you do angular momentum conservation? When the net external torque is zero. So if there is no net external torque, then better the angular momentum is conserved. So now let's do some important points about the angular momentum conservation. First of all, starting with our mother earth. So if the polar ice cap melts, we have done this in moment of inertia. If the polar ice cap melts, there are mountains of ice at the Arctic and at the Antarctic. If the polar ice cap melts, the ice will convert into water, and because of which the sea level will rise, the water will move even towards the equator. As the mass goes away from the axis, moment of inertia will increase. We know that there is no external torque acting on Earth. So its angular momentum should be constant, and we know that angular momentum is I omega. So as the ice converts into water and move away from the axis of rotation, you can say moment of inertia will increase, so the angular velocity of Earth should decrease. When I say that the angular velocity of Earth should decrease, it means that now the Earth should rotate slowly. If the Earth starts rotating slowly, if the omega of Earth decreases, what will happen to the length of the day? The slower the Earth spins, the longer will be the length of the day. Here we have Sun, here we have Earth. Think of a point on the Earth. When this point is closest to the Sun, we say we are at noon. The faster the Earth spin, the lesser will be the duration of one day, and the slower the Earth spin, the more will be the duration of one day. So if polar ice caps melt, moment of inertia of the Earth will increase. As the moment of inertia of the Earth will increase, we know that angular momentum for a pure rotating body is I omega. So as the moment of inertia will increase, omega will decrease. So from L equals to I omega, we know that as moment of inertia will increase, the omega will decrease. And if the omega of Earth decreases, then the Earth starts turning slowly. So the length of the day will increase. So the Earth spins slowly and the length of the day increases. Second case, on building tall skyscrapers, we are constantly constructing tall building. When you construct a tall building anywhere on Earth, let's say in India, what do? We take some raw material and build a building. So you are moving the mass away from the axis or towards the axis. So we dug up concrete and iron and everything, and we are constructing a building. So we are moving the mass away from the axis. As you are moving the mass away from the axis, you are increasing the moment of inertia of Earth as we construct a building, or are we decreasing it? So we are increasing the moment of inertia. Mass is moving away from the axis. So on building tall skyscrapers, moment of inertia of Earth increases. Again from L equals to I omega. As the moment of inertia of Earth is increasing, the omega will decrease. And as the omega will decrease, the Earth will start spinning slowly. And as the omega of Earth decreases, the length of the day will increase. So you will say, so the Earth spins slowly and the length of the day will increase. Okay. Now let's see more example on angular momentum conservation. So the next example, an astronaut spinning in space folds his hand. So there is an astronaut and the astronaut is spinning in space. Now the astronaut folds his hand. What happens to his angular velocity and rotational kinetic energy? So what will happen to the omega and what will happen to the rotational kinetic energy? So it's obvious that if the astronaut folds his hand, he is moving mass closer to the axis of rotation. So when astronaut folds hand, the mass moves closer to the body and hence the moment of inertia will decrease. Now once you know that the moment of inertia will decrease, okay, on folding the hand, and there is no external force, no external torque acting on him, from L equals to I omega, you can say as the moment of inertia decreases, the omega will increase. So as no external torque acts, angular momentum is constant. So from L equals to I omega, as I will decrease, the moment of inertia will decrease, the omega will increase. So this answers our first part of question. What will happen to the angular velocity by when the astronauts moves the hand closer to the body, the omega will increase, the astronaut will start spinning faster. Now next question is, what happens to the kinetic energy? Just like we know that P equals to mv, yes. Kinetic energy equals to half mv square, yes. That can be even written as half into m square v square by m. That can also be written as p square by 2m. Similar type of things can be done for rotational as well. We know that angular momentum equals to I omega. Rotational kinetic energy is equals to half I omega square. So that can be written as half I square omega square by I. That can be written as L square by 2I. So just the way we write translational kinetic energy to be equals to P square by 2m, we can even write rotational kinetic energy to be equals to L square by 2I. So from kinetic energy equals to L square by 2I. Tell me, when the astronaut folds the hand, what happens to the angular momentum? Does it increases or decreases? Sir, we are learning angular momentum conservation. There is no external torque acting. So the angular momentum has to be constant now. Okay, sorry. So L will be constant. what happens to the moment of inertia? So as the person folds the hand, the moment of inertia decreases. So from L square by 2I, L is constant, but I decreases. So everything is constant, the denominator decreases. So you will say, sir, kinetic energy increases. So as L is constant and moment of inertia decreases, the kinetic energy of this astronaut as the astronaut folds the hand will increase, as well as the omega will increase. Let's see the next example. A person of mass m is standing at the center of a disk of same mass. A person of mass m stands at the center of a disk of same mass. So person has mass m, disk has mass m. Now, rotating about its axis with an angular velocity omega. So this whole system is rotating with an angular velocity omega. If the person moves from the center of the disk to the periphery, determine the final angular velocity. First thing first, as the person moves from center of the disk to the periphery of the disk, what will happen to the moment of inertia of the system? So sir, since the mass is moving away from the axis, the moment of inertia will increase. So from L equals to I omega, I can say with cent% guarantee, as the moment of inertia is going to increase, omega, the angular velocity, is going to decrease. This is sure. Now how much will be the value? It's not rocket science, it is easy to calculate. So let's calculate it. So let's think of the initial case. When the person of mass m stands at the center of the disk and the whole system is rotating with an angular velocity omega, and then think of the final case when the person has reached the periphery. Now let's say the whole system rotates with an angular velocity omega dash. We can do angular momentum conservation. We can say initial moment of inertia into initial omega equals to final moment of inertia of system into final omega. So we can say L equals to I omega. From angular momentum conservation, initial moment of inertia into initial omega. When you write the initial moment of inertia of the whole system about this axis, how will you write? You will say, sir, the whole mass of person is on the axis. So the distance of the mass of the person from the axis is 0. So when we write the initial moment of inertia, there will be no contribution of the mass of the person. So that will be m into 0 square. This is the moment of inertia of the person about the axis. Since the entire mass of the person lies on the axis, there will be no moment of inertia because of person. Now how to write the moment of inertia of the disk? So sir, that will be mr square by 2. This is how you write the initial moment of inertia of the system. How will you write the final moment of inertia? So finally the person is on the periphery. So the person is at a distance r. So the moment of inertia of the person will be mr square. While the moment of inertia of the disk is same, which is mr square by 2. It is given in the question that the person and the disk has the same mass. That's why I have taken both the masses as m. So you can say I1 omega 1 initial moment of inertia into initial omega equals to I2 omega 2 the final moment of inertia into final omega. Initial angular velocity is given to us as omega, and we have assumed the final angular velocity as omega dash. So we can write initial moment of inertia, which is mr square by 2 into initial omega, has to be equals to final moment of inertia, which is mr square plus mr square by 2 into omega dash. So beta, this mr square plus mr square by 2 is nothing but 3 mr square by 2. So on the left hand side you have got mr square by 2 into omega. On the right hand side you have got 3 mr square by 2 into omega dash. Cancel out mr square by 2, mr square by 2. So you simply get omega dash equals to omega by 3. So as the moment of inertia becomes 3 times, the angular velocity becomes 1/3. Let's practice more question on angular momentum conservation. So the question goes like this. A ring of mass m rotates in space with an angular velocity omega. If four small plastine drops of mass m dash each are placed on its periphery, determine the angular velocity of the ring after placing the drops. So first visualize that there is a ring of mass m and radius r rotating with an angular velocity omega. Now on this ring we have placed four small plastine drops, each of mass m dash, and we have to tell what will be the new angular velocity. Okay, so visualize the final case when we have placed four small plastine drops. I have shown them with the red points here, and let's say the final angular velocity of system is omega dash. But the angular momentum conservation is one of the easiest thing. All you have to do is initial angular momentum equals to final angular momentum. So you will say, as no external torque acts, as the external torque is zero, angular momentum is constant. So you can simply say I1 omega 1 equals to I2 omega 2. That is the meaning of angular momentum conservation. So all you need to do is write the initial moment of inertia into initial omega equals to final moment of inertia into final omega. Initially, you have just one ring of mass m and radius r. Its moment of inertia will be mr square by 2 into the initial angular velocity omega. Now on the ring, once you have placed 4 drops, each of mass m dash, and I ask you, now tell me what is the moment of inertia of this system about the axis. You will say, sir, to write the moment of inertia, I have to consider both the ring as well as the masses. Because of the ring, the moment of inertia will be mr square. Because of the 4 small masses, plastine drops, the moment of inertia will be 4 into m dash into r square. So this will be the final moment of inertia. So initial moment of inertia mr square into initial omega equals to final moment of inertia, that is mr square plus 4 m dash r square into the final omega. Now bachcho, our mission is to find the final omega. Cancel out r square, r square, r square. So you get omega dash equals to m omega upon m plus 4 m dash. So that's not a tough question. Okay, all you need to do is write the initial moment of inertia carefully and final moment of inertia carefully about the same axis. So let's practice a different type of question based on angular momentum conservation. So this is the question. A boy of mass m moves tangentially with a speed v and jumps on a merry-go-round in the shape of the disk of same mass m. So there is a boy of mass m. He goes and jumps tangentially on a merry-go-round. We are looking from top. Okay, we are eagle. We are a bird. We are looking from top and we see that there is a merry-go-round and there is a guy coming and he jumps tangentially over the merry-go-round, and because of that the whole merry-go-round and the boy starts to rotate. So once more question. A boy of mass m moves tangentially with a speed v and jumps on a merry-go-round in the shape of a disk of the same mass m as the boy and rotates with it. Determine the angular velocity of the merry-go-round and the boy system. So there is a boy. We are looking from top and this is the merry-go-round. The boy comes with a speed v, jumps tangentially and sticks to the merry-go-round, and then this whole system starts turning with an angular velocity omega. You have to find this omega given that the mass of the boy is same as the mass of the merry-go-round, which has to be treated as a disk. This is not a tough question. So let's see what to do. So first of all, look from top. So from top, this will be the condition before the boy jumps and sticks with the merry-go-round. And once the boy has jumped and has stuck here, the final condition will look like this. So there will be boy, there will be merry-go-round, and they will be rotating with a common omega as seen from top. So all you have to do is angular momentum conservation about the hinge. Now here you will have to write 2 types of angular momentum. Understand that before the boy jumps, there is no pure rotational motion, right? The person does translational motion. So we are going to do angular momentum conservation about the hinge. You will say before jumping, what is the angular momentum of the disc of the merry-go-round? So you will say, sir, the merry-go-round is at rest. So the merry-go-round has no angular momentum about the hinge. But this boy's motion has some angular momentum about the hinge. How to write? Extend the line of momentum of boy and find the distance perpendicular. So the angular momentum of this boy about the hinge before jumping will be momentum times mv times length perpendicular, which is r. After jumping, once the boy sticks with the merry-go-round, now the whole system performs pure rotational motion. And the angular momentum for this pure rotational motion will be moment of inertia of the whole system into omega. And you know how to write the moment of inertia of this merry-go-round and the person system once the person has jumped. So you will write, doing angular momentum conservation about the axis of the merry-go-round. The initial angular momentum before jumping, momentum times length perpendicular mvr, equals to the final angular momentum once the boy sticks. Now once the boy sticks, the merry-go-round and the boy does the pure rotational motion. Their combined moment of inertia will be mass of boy is at distance r. So that will be mr square. This will be the moment of inertia due to the boy. And due to the merry-go-round assumed as a disk, its moment of inertia will be mr square by 2. So the overall moment of inertia is mr square plus mr square by 2, which is 3 mr square by 2. So this has to be equals to mr square plus mr square by 2. This is moment of inertia of the whole combined system times the angular velocity with which this whole system will move. Now once this is done, you can find out omega easily. So mvr equals to 3 by 2 m r square into omega. Cancel out one term of m, one term of r, so you get omega equals to 2v by 3r. So that will be the angular velocity of the person and merry-go-round system. So that's all in this hour. In the next hour, what we are going to do is the best part, that is the combination motion, rolling. So see you guys in the last hour of rotational, and where we will learn about rolling. Hope you like this. Please share and subscribe. See you guys. Bye bye. So that's all for now. See you guys in the next hour.